When engineers look at a signal, there are two completely different ways to view it. One view shows how the signal changes over time. The other reveals the frequencies hidden inside the signal. Both describe the same signal, yet each provides insights that the other cannot. Understanding these two perspectives is one of the most important skills in RF engineering. In the real world, signals are observed as changing voltages, currents, or electromagnetic waves over time. Engineers can easily measure these variations using oscilloscopes and other instruments. This time-based representation provides useful information about amplitude, timing, and waveform shape. However, many important RF problems cannot be solved simply by looking at signals in the time domain. For example, determining bandwidth, identifying interference sources, analyzing filters, or understanding modulation schemes often requires knowledge of the signal's frequency content. This creates a challenge. A signal may appear complicated when viewed over time, but become much easier to understand when viewed in terms of its frequencies. Engineers therefore need a second perspective that reveals information hidden from the time domain view. The time domain represents a signal as it changes over time. In this view, the horizontal axis is time, and the vertical axis is usually amplitude. This is the most natural way to observe physical signals, because real signals exist and evolve over time. The frequency domain represents the same signal in terms of its frequency components. Instead of showing when changes occur, it shows which frequencies are present and how much energy exists at each frequency. This view reveals the spectral structure of the signal. Although these two representations look very different, they describe exactly the same physical signal. They are simply different perspectives that highlight different aspects of the signal's behavior. Intuitively, consider listening to a musical chord played on a piano. Your ears hear a single sound over time, which is analogous to the time domain representation. However, that chord actually consists of multiple musical notes occurring simultaneously. The frequency domain reveals those individual notes. Physically, a transmitted RF signal may appear as a rapidly oscillating waveform when observed on an oscilloscope. While the waveform itself may seem complicated, its frequency domain representation immediately shows the carrier frequency, sidebands, and bandwidth. Mathematically, every sufficiently well-behaved signal can be represented as a combination of sinusoidal components. Fourier analysis provides the mechanism for converting between the time domain and the frequency domain, allowing engineers to study signals from either perspective. Time domain analysis is useful when engineers need to examine waveform shape, pulse timing, transient behavior, or signal delays. Oscilloscopes are commonly used because they display signals directly in the time domain. Frequency domain analysis becomes essential in RF engineering because wireless systems are fundamentally organized around frequencies. Engineers use spectrum analyzers to observe carrier frequencies, bandwidth, harmonics, interference sources, and spectral efficiency. At the system level, filters are often easier to understand in the frequency domain, while transient behavior is easier to understand in the time domain. Successful RF engineers learn to move between both views depending on the problem being solved. Neither domain is universally superior. The time domain provides clear information about when events occur, but frequency information may be difficult to extract directly. The frequency domain reveals spectral content clearly, but may hide timing information. A common mistake is assuming that one representation contains more information than the other. In reality, both domains describe the same signal. The difference lies in which characteristics become easier to observe and analyze. This dual representation forms the foundation of modern signal processing. The next lessons on Fourier series and Fourier transform will explain how engineers mathematically move between the time domain and the frequency domain, and why these tools are so powerful. In this lesson, we learn that signals can be viewed in both the time domain and the frequency domain, with each representation revealing different aspects of the same signal. We also saw why RF engineers frequently switch between these perspectives when analyzing communication systems, filters, and wireless signals. In the next lesson, we will explore Fourier's series and discover how complex periodic signals can be built from simple sinusoidal components. If you found this useful, like the video, subscribe, and follow for the next lesson.